Yeah, good morning to everyone. Good morning, everybody. Okay. Rahul, am I audible?
Yes, sir.
I hope I'm audible. Okay, good. So, my dear student, today I'm going to start a third unit. Okay. Strain energy. Using a strain energy concept, principle, how do you determine stresses induced in the material of the given body? Okay. And then what is the strain energy stored when the body is subjected to tensile and compressive action, when the body is subjected to bending action, when the body is subjected to torsion? What is the strain energy stored in it? Okay. What is the application of that concept? Like that, likewise, we are going to see in the third unit. Okay. Just I will share my notes, which was prepared long back, right? No problem, right? This is the notes. Very good. Strain energy in tension and compression. Strain energy, this is unit 3, keep it in mind. Strain energy in tension and compression. Okay. First, we will start with simple tension and compression. I have a body, okay, a prismatic bar. It is subjected to a pulling action, right? Whose length is L, subject to pulling action, right? I am plotting, say, at any instant of time, the load acting on it is, say, P dash. The corresponding deformation in the bar is del dash, okay? So I am taking a plot. In the abscissa, I am taking the deformation del dash. In ordinate, I am taking this force applied P dash. I am plotting it. We know very well the Hooke's law. Within the elastic limit, the stress is proportional to strain. Okay. In other words, within the elastic limit, force is proportional to deformation because the material behaves linearly within the elastic limit. Okay. So I am applying the load. I am plotting it. What happens when the load increases? Okay, when the applied load on the bar increases, the deformation also increases proportionally. That is why you are getting a straight line, linear combination, linear behavior like this. Okay, up to the limit of proportionality. Hereafter, the material bar starts behaving in a elastoplastic manner. Okay, so up to limit of proportionality, we stopped. Now we are within the elastic limit. Okay, it obeys Hooke's law. Very good. This is the plot. So the ultimate load is P on the bar. Ultimate means the proportional load at the point of proportionality is capital P. Okay, the deformation at the point of proportionality is del. Okay, capital del. I have a plot here. Now what happens when you apply load? Okay, the force does some work, isn't it? You are applying load. There going to be displacement, deformation in the bar. That is the work done. Some work is the force does some work. Okay, when you remove the load, what happens? If you suddenly withdraw the load, what will happen? The bar regain its original dimension, original position. Okay, original shape again. It regains. How does it regain? Actually, to deform the bar, we applied an external load, external force. We pulled it. Okay, we applying some energy force. We pulled it in order to cause the required deformation, not to cause the deformation, whatever deformation has come. Okay, but if you withdraw the force, the bar again goes back to its original position. The property is called elasticity. You know very well what is elasticity. Okay, how does it go? Okay, for that some force, some energy required, no, to because to deform it, some force, energy, external energy is required. Again, to when you suddenly withdraw the external force applied on it, it regain its original shape. Again, some energy is involved in there. Okay, that energy is called strain energy. Okay, so the work done, whatever work we do on the body, it is stored in the body in the form of strain energy. Okay, that strain energy is spent to bring it back to its original dimension. So you know very well what is elastic material. Okay, an elastic material undergoes deformation when subject to an external loading, such that the deformation disappears on the removal of the loading. This fact you know very well. Okay, what is elasticity? This property is called elasticity of the body, right? This you know. So within the elastic limit, this way the mechanism takes place. Okay, please keep it in mind. Again, to bring back the body, as soon as we withdraw the low force or load acting on a body, the body regain its original dimension or original shape by how to say, by using that dissipate, okay, by dissipating or by utilizing the energy stored in the body in the form of strain energy. That is called strain energy. Okay, let us see how do we see the explanation what I have written. Work done by the load P dash for an increment dP dash. Okay, now we are not seeing the full workload. At any instant, say the force is P dash. Okay, because the P starts from 0. Okay, because when you pull the bar, initially you are starting with 0 force, and then gradually you are increasing the magnitude of the force. Okay, later only to achieve capital P force. At any instant, the force is P dash. Okay, so a particular instant, the force acting on the bar is P dash. Okay, so the increment, small increment in the incremental deformation is say dP dash. Okay, so the work done is equal to P dash into D del dash. Otherwise, work done by force P dash for an increment, dP dash means increment in the force. The corresponding deformation is D del dash. Okay, so the P dash into D del dash is the work done. Okay, represented by area of the standard strip. Here it is represented. What is this P dash and D del dash? See, here I at the force P dash I am taking here. At any instant, the force is P dash here. The corresponding deformation in the bar is del dash. Thereafter, there is a 1 minute. Some latecomer has come. Okay, automatically. Okay, right. So here, the increment deformation is d del dash, right? Right. Now, what is the work done here? Which is I have written P dash into d del dash, which is nothing but just to have a look at the graph. This is what is P dash? This ordinate here. The average ordinate here is P dash. Okay. Actually, I have shown up to this. Strictly speaking, it is up to the center. Okay. The average P dash is ordinate is P dash here into d del dash, which is nothing but the shaded area. Okay, that is the work done. This shaded area is nothing but the strain energy stored, right? For the force capital P, the total deformation is capital this del. Okay, so the area, the total area under the curve, under the line, okay, under the linear line here will be the energy stored, right? Let us see that the discussion and all we see here. This work represented by the area of the shaded strip in the figure is stored in the bar in the form of potential strain energy. Okay, potential strain energy means what? It is energy is there, potential energy. As soon as you withdraw the force, that the potential energy will be utilized to bring back the bar. Okay, if the increment of load dP dash is removed, the lower end of the bar moves up through the distance d del dash, and the stored energy P dash d del dash is transformed back into the work of raising the external load P dash through the distance d del dash. So explanatory manner it is given for your understanding, right? Thus, we may regard the elastic bar as a spring in which energy can be stored or released accordingly as the load P dash is increased or decreased. Okay, now the elastic bar acts as a spring in which energy can be stored or released. Okay, elastic spring, it's act as a elastic spring. It is this all this factor already you may aware of it. Okay, the total energy stored in the bar of figure under a tensile load P is equal to the sum of all such elemental steps as P d del dash between O and B, and is represented by the area OAB in figure. This what? Okay, area OAB. So the total for the force P, the total energy is you have to add all such elemental areas here. Okay, so the full area, just hand tool I will take. You will be getting this full area. Okay, this full area you will be getting, right? Area under this curve will be the energy stored, total energy stored, right? So the total strain energy stored U equal to what is the area here? How do you get this area here? This is P, this is del. Okay, this is P, this is del. P into del. Okay, what is the area of this triangle? which is half P del, isn't it? It is half P del. This is P, this is del. Base is a del, vertex is P, capital P. Okay, therefore, the area of this triangle is half P del. That is total energy stored. We are using a notation capital U to represent total strain energy, potential energy. In other words, potential energy. The total strain energy is nothing but the potential energy stored in the bar. We are using the notation capital U. Keep it in mind. Capital U is equal to P del divided by 2. This is valid only if Hooke's law applies. Okay, this is valid only if Hooke's law applies. We also know that is del equal to PL by AE. We know within the Hooke's law, we have the deformation in the bar. Del is equal to PL by AE, or from this I can write P is equal to del AE by L. We can say this way or that way, isn't it? We know the deformation in the bar del equal to PL by AE. From this, I am writing P. P is equal to del AE divided by L. Okay, this way. Now I am rewriting this strain energy stored. Therefore, U is equal to, substitute in this del equal to PL by AE. If you substitute here, P into P, P square, L divided by, 2 is already there, 2 AE. Okay, P square L by 2 AE. Or U is equal to, you substitute P equal to del AE L in this, okay, in this. So instead of P, you substitute this value. So AE del square, already del is there, here one del is there, so del square divided by, already 2 is there, denominator L is there, 2L, okay. So this expression you will be getting. Here, what is this? The strain energy per unit volume we are getting. This is the total strain energy stored in the bar. When at the limit of proportionality, when the maximum load is applied on the bar, at the limit of proportionality, this is the strain energy stored for the entire volume of the bar. Total strain energy stored for the entire volume of the bar. I am interested in determining the strain energy stored per unit volume of the bar. Therefore, that is equal to capital U divided by AL. A is what? Area of the cross section of the bar into L, which is nothing but volume of the bar, right? So I want the strain energy stored per unit volume. So what to do? The total energy, you have to divide that by the volume of the bar. Okay, that's why UU by AL. That is U equal to sigma square by 2E. What is that sigma? How do you get? If you substitute AL here, which one? If you divide this by AL, what will happen? LL get cancelled. A become A square. What is P square by A square? What is P by A first of all? P by A is nothing but sigma. Yeah, we know stress. So sigma square, right? Divided by 2E. Because AL you are substituting here, no? See here, you substitute, you divide this by AL. You divide this expression by AL. What will happen? LL get cancelled. A into A become A square. P square by A square is, you can write it as sigma square. So sigma square divided by 2E. Sigma square divided by 2E. Or U equal to, you substitute in this, right? What is that? You divide this by AL. You divide this U by AL. So AA get cancelled. Here L square, okay. What is del by del square by L square, or what is del by L? Change in length by original length is nothing but strain square. So capital E into strain square divided by 2 alone is the denominator. So 2. Okay. So sigma square by 2 either you can say, or E small e square by 2 you can say. The strain energy stored per unit volume of the body. Okay. So this expression is important. The strain energy stored per unit volume of the body when it is subject to either tension or compression is sigma square by 2E. You should remember. Okay, the strain energy stored is sigma square by 2E. This is very important. I advise all of you to memorize. Okay, strain energy stored per unit volume is sigma square by 2E. The strain energy stored per unit volume, there is another name. What it is? Let us see. The greatest amount of strain energy, keep it in mind, the greatest amount of strain energy per unit volume that a material can absorb without exceeding its proportional limit can be found by substituting this proportional limit for sigma P, suffix PL means proportionality limit. Stress value in proportional, at its proportional limit. in U. That is U equal to sigma square by 2E. In this, if you substitute, you can determine the maximum strain energy that can be per unit volume. The greatest amount of strain energy that can be stored per unit volume can be determined of a body. This quantity is called the modulus of resilience of the material intention. Modulus of resilience. Please, all of you, remember this modulus of resilience. In the competitive examination, when you go future, if you appear gate exam or some other appointment you apply, written test will be conducted. It is a usual question. What is the modulus of resilience? So you immediately have to say it is the greatest amount of strain energy that can be stored per unit volume of the body. Okay. The moment you say greatest strain energy means the stress in the body will be at the limit of proportionality, proportionate limit stress. Okay. So maximum stress, that is the maximum stress that can be occur. Okay. At the limit of proportionality, what is the stress? You have to substitute that one in the sigma, in the sigma square by 2E. Okay. So that is called modulus of resilience of the body. And also there is another word called proof resilience. What is proof resilience? Proof resilience is nothing but the greatest amount of energy that can be stored in the entire volume of the body. How do you get it? Sigma P suffix PL means proportional limit. Sigma value at proportional limit. Stress in the body at proportional limit. Okay, square divided by 2E, that is modulus of resilience into volume AL. Volume of the body. Volume of the body is AL. If you again multiply it by volume, that is called proof resilience. Okay. Now I have introduced two terminologies, two technical terms to you. One is modulus of resilience. Another one is proof resilience. What is modulus of resilience? Modulus of resilience is nothing but the greatest amount of strain energy that can be stored, okay, per unit volume of the body without exceeding proportionate limit. Okay, of the body, of the material of the body. Right. The next one is what is proof resilience? It is the greatest amount of strain energy that can be stored the entire volume of the body. Okay, not per unit area. The entire volume of the body without exceeding proportionality limit. This way you can give explanation. Right. Now for steel, the proportional limit is 200 Newton per mm square. Actually, I prepared these notes by referring elements of strength of materials by Timashang Ondiang. I think this notes was prepared when I 1993. In 1993, when I was teaching elements of strength of materials, that time I prepared, I think. Okay, that time I referred that elements of strength of materials by Timashang Ondiang. That book is in MKS unit, not in SI unit. That is why I have written like this. Okay, but you keep it, take it in SI unit. Stress at limit of proportionality PL is equal to 200 Newton per mm square. Modulus of resilience you will be getting accordingly. Unit conversion required to be done here. Okay, no problem. We are not interested on that. The foregoing discussion of strain energy can be used also in the case of axial compression. Okay, whatever we have discussed so far, when the bar is subject to axial tension, the same thing is applicable for axial compression also. The only difference is, but sigma and E are negatives. The only difference is the stress value and the strain values are negative, but it appears to the square in expressions. Okay, since we are writing the strain energy stored, modulus of resilience is equal to sigma square by divided by 2E. No, sigma square is there. Similarly, E square is there. Strain square, stress square is there. When you deal with the compression, when you substitute this sigma and E in with negative sign, because it is in square, so it becomes positive quantity. Okay, but it appears to the square in the expression. This has to okay, this has no effect on the final result. So in short, strain energy is always a positive scalar quantity. So in short, strain energy is always a positive scalar quantity. Okay, so either you deal with the tension or compression, strain energy value will be the same. Okay, right. We will see its application. Let us start with simple thing. Stresses due to various types of axial loads. Okay, stresses due to various types of axial loads. So I am going to discuss here. Okay, suppose you all are aware, you all know very well that suppose a bar is subject to gradually applied load. How to compute stress at any instant? You know very well. the load acting on the bar at that instant divided by the original area of cross section will give you the stress induced in the material. This way you will compute the stress. Okay, this procedure you know very well. Suppose the bar is subjected to suddenly applied load. The load is not gradually applied on the bar. It is suddenly applied. What will be the stress induced? How do you compute it? You don't know. Okay, now you are going to study by using this energy principle, this energy, strain energy concept. Okay, you are going to determine now. Suppose the body is subject to impact load. Weight, you have some weight, you are not keeping the weight on the body, you are allowing it to fall from some height on the body. You have some weight, you are allowing that weight to fall on the body from a particular height. In that case, what will be the stress induced in the material of the body? When some weight is kept on the body, you know how to compute the weight. Okay, that weight divided by area of cross section of the body will give you the stress. But if the weight is allowed to fall from some height, what will be the stress induced? That is impact force. When the body is subject to impact force, the stress induced in the body will be different. How do you get it? How do you compute it? To do such computation, we are going to use this strain energy. Okay, let us see how. Now, gradually applied force. First, we are seeing gradually applied force means what? Initially, the force is zero. When you are increasing the force, gradually you are applying, it reaches capital P. Okay, final load acting on the bar is capital P. That time the deformation will be del. Okay, del. So it deforms, the bar deforms to an amount del here. Okay, so shown here. The bump, that's a deformation in the bar. During its deformation, see the deformation is very minute, right? For visualization purpose, I have drawn this much. This is the deformation. At zero deformation of the bar, the force acting on it is zero. At del deformation of the bar, the force acting on it is P, capital P. The force gradually increasing. Okay. So work done is equal to what? Half into P del. What is the work done? This one, half into P del. In other words, average force. What is average force? 0 plus P divided by 2. P by 2. Okay. The average force is 0 plus P divided by 2. Okay. P by 2 is the average force here. Right. That into del is the work done. So half P del is the work done. Strain energy stored by the member is equal to, just we are writing this way. What is the strain energy stored by the member? Is equal to work done by the external load, which is written here. Strain energy per unit volume. What is the strain energy stored by the member? Which is nothing but strain energy per unit volume into volume of the rod is equal to average load into extension. Work done is nothing but average load into extension. That is, we already know the strain energy stored per unit volume of the body. That is modulus of resilience. We already know, which is sigma square by 2E into volume of the body, AL. This is the total strain energy stored per the entire volume of the body. Okay, the strain energy stored the entire volume of the body. How do you get? Already we established the strain energy stored per unit volume of the body, which is sigma square by 2E into area of the bar is AL into AL is equal to half into P del, the work done. Average load into P by 2, that is average load into the deformation, extension, del. Okay. So, but del is equal to, here I have written, but del is equal to sigma L by E. How del is equal to sigma L by E? You know all very well. The deformation del is equal to PL by AE. Okay, instead of writing PL by AE, P by A I have replaced as sigma. Sigma L by E. Okay, both are one the same. Either you write PL by AE or sigma L by E, both are one the same. Substitute this del is equal to sigma L by E. So, from this we are getting sigma equal to P by A. We are getting correctly. Okay. So the stress induced in the material will be P by A. How do you get the stress induced in the bar when it is subject to gradually applied load, which is P by A? You already know by energy principle we got it. Okay. Let us see. In a similar way we can get the stress induced for another type of loading also. I am going to suddenly applied load. If the load is applied suddenly, let the load P be suddenly applied. Let the extension of the member be del, small del. Okay. In this case, the magnitude of the load is constant at P throughout the process of extension. Right. Strain energy stored in the member is equal to work done. Let us see. The load is suddenly applied. There is a sudden deformation in the bar 0 to del, it deforms. During its deformation, the load is constant throughout because it is suddenly applied. Okay. So therefore, the work done is equal to P into del only. not half into P del. It is P into del, okay, because it's suddenly applied, P into del only. Now, sigma square by 2E, so strain is stored per unit volume into AL. The volume of the body will give you strain is stored in the entire volume of the body is equal to P into del. I have written here, P into del. Again, I am reading sigma square by 2E into AL is equal to P into, what is del? Del equal to sigma L by E. Already we know, sigma L by E substituted. From this, sigma is equal to 2P by A, we are getting. So, the stress induced is twice, okay, when the same load is applied gradually. When the same load is applied gradually, whatever stress induced in the bar, twice that stress will be the case if the load is applied suddenly. Okay, that is what? Sigma equal to 2P by A. Hence, the maximum stress intensity due to suddenly applied load is twice the stress intensity produced by the load of the same magnitude applied gradually. Hence, the maximum stress intensity due to suddenly applied load is twice the stress intensity produced by the load of the same magnitude applied gradually. Okay, so that is the conclusion we made. Next, impact load. I am coming to impact load. It's a very interesting case, right? So you'll be getting some problems with the impact load, right? So we have the same bar. Just some provision is there. So the weight can slide along the bar and fall down. Okay. And another special provision is there. We have a collar here or flange here. Okay. To absorb this one, right? So because tension, no. Okay. Let us see. So this is the provision. This way it is falling. Some collar is there at the bottom of the bar. On that, this weight is falling, right? Due to that, the bar extends like this along with the collar. It extends like this. So the deformation is del, right? It is falling from a height h, small h. The length of the bar is L. The weight is capital W, right? Let us see. This is the deformation. Now, strain energy stored by the member is equal to work done. Work done is nothing but loss of potential energy. Let us see. So, strain energy stored by the member is equal to sigma square by 2E into AL. You know, which is equal to, what is the work done? The W into H plus del. Actually, the weight falls and the collar moves down, no, deformed down, no. So the weight goes up to this. Then afterwards it comes to rest. So the work done is H plus del. That is the that much distance the weight moves. H into del. Okay, W into H plus del. But del equal to sigma L by E. You know. Now you substitute. Okay. Sigma here, some striking, because roughly I have prepared this notes long back. No problem. Sigma square by 2E into AL is equal to W into H plus, this is del is equal to del, sigma L by E, I am substituting, right? Now, we have to do something, let us see. Just I am writing in an expanded manner, sigma square by 2E into AL minus, what is that minus? I am multiplying it. The WH, I am keeping it in the RHS side. This W into sigma L by E, I am bringing into LHS side. Okay, so it can become minus W sigma L by E. Okay, here we are bringing, this way we have written. Now we have to do something to modify this equation. Okay, multiply, because you know in an equation you can do whatever you want. You can RHS, LHS, you can multiply with any term, you can divide it with any term. This mathematical law and all you know very well. Okay, so according to our requirement, we are doing the things. Multiply by 2E by AL throughout, okay, because I want to get the expression for sigma. Okay, from this sigma is appearing at two places. It looks like a quadratic equation. Sigma square is there, sigma is there, right? I want to get to that sigma. For that, what I am doing, multiply by 2E by AL throughout, because here sigma square is there. So this I want to remove this. Okay, so 2E, if I multiply this equation by 2E by AL, this will be get removed. That's why if I multiply sigma square minus, if I multiply this by 2E by AL, it becomes 2 sigma, 2 W sigma by A. Later you think over how this E get cancelled. Okay, 2 W sigma is there. Okay, A only you are multiplying, no. E, A is there. Here E is supposed to be there. The E is taken that side. Here E is how it can be taken. Oh, sorry. Actually, yeah, multiply by 2E by L. Oh, E get cancelled. I'm sorry. 2E by L, no, E get cancelled here itself. Right? Right only. 2W sigma by A alone will be there. Is equal to W into H into this 2E by AL, okay, multiplied here. This way you are getting it. Now, adding W square A square to both sides of the equation, because I want to bring it to a compact form, a particular standard form. That's why I'm doing further adding W square by A square to both sides of the equation, right? So just in this equation, we are adding it, W square by A square. Okay, here also W square by A square, we are adding it. So finally, A square plus B square plus 2AB, this form it comes. Why W square A square we are doing? Because we are observing this equation, right? So it looks like A square, 2AB, B square, that form we bringing. That is why if I add it, it becomes that form. That's why A minus B whole square, A square minus 2AB plus B square, it is in this form. That is why sigma minus W by A whole square, okay, A minus B whole square is equal to W square A square plus it is as it is, RHS is as it is. Okay, from this sigma minus W by A is equal to root of this RHS. Therefore, sigma equal to W by A plus root of W square by A square, or you can write W by A whole square also, you can write here, no problem. W square by A square plus 2WHE divided by AL. This is the equation. Okay, this is the expression, equation number 1. So you have to use this expression. You have to use this expression in order to compute the stress induced in the material of the bar when it is subjected to impact force. Okay, when if your bar is subjected to impact load, you have to use this expression for determining. No any other go, you have to memorize this equation. I advise all of you memorize this equation. Okay, being a student, you can memorize so many things. Please memorize it. When del is very small in comparison with the H, okay, please see here. When del is very small in comparison with the H, loss of potential energy work done is equal to W into H. We can, in short, we can determine. This is determining accurately. Okay, the stress induced in the material so accurately. Okay, sensitive cases we can determine this way. No, sir, I don't want to determine accurately the stress induced. What is the stress induced? Because when the bar is subjected to impact force, the deformation is very negligible when compared to the height from which it falls down. So I want to neglect del means this is a short way you can determine. How? This is sigma square by 2E into AL. Okay, the total strain energy stored is equal to work done, which is W into H. We are neglecting H plus, instead of writing H plus del, we are writing only W into H alone. Now easily you can get it. Okay, therefore sigma equal to root 2WH by EE, signed equation. This equation also you can use to determine stress induced in the bar when it is subject to external loading. Please all of you remember, this is the actual expression, very accurate expression. This is approximate. Equation 2 is approximate expression for determining stress induced. 2WHE by L, this one, the last term, root of 2WHE divided by AL. This one you remember. Okay, when just another discussion, when H is equal to 0, it's not falling from height. That means what? Suddenly applied load. Okay, when H is equal to 0, the equation 1 becomes here. In this you substitute H is equal to 0, so equation 1 becomes this way, which is 2W by A, which is the case of suddenly applied load. Okay, which is the case of suddenly applied load. We are also clarifying, validating the equation. We are also validating it. Okay, so we got an expression for impact load. Suppose the weight is not falling from a height H, it is suddenly kept on the collar. Okay, what will happen? So H becomes 0 in this. If substitute H is equal to 0, you are getting the case of suddenly applied load. Just now we have seen 2P by A, we have seen here 2W by A, which is the case of suddenly applied load. This way we are validating the expression obtained. Okay, so that's all. Using the concept, we can do a lot of numerical problems. Okay, I think this much is sufficient for today's class. Next class we will see the problems. Okay, because you may problems are plenty. Okay, not plenty. Next one is strategy due to torsion. It's okay. The problem I will do it in the next class. We will discuss it in the next class. Okay, first I will stop and then I will do a certain discussion. First, let me to record the names for attendance. For attendance purpose, I want to record your names. Nearly 45 of you are attending. Very good. Just I want to record your name for attendance purpose, right? Let it be recorded. Definitely, okay. I have to send you the notes. No, I have been telling words, but I am not sending. Today, I will do my best to send you the notes, right? Whatever we have discussed so far, all the notes I will send it by today. First, let me to stop recording. Then we will discuss something. Okay, let us wait.